Okay. Okay. Thanks everyone. It's a great honor to stand here to present to share our work in the for urban canopy flow. And this work is my co-author will be Professor Minping and Professor Shiyi. Now let's go back to urban canopy flow. I think everyone has recently these days has hearing about the higher layer of the atmospheric bound layer. So let's come back to a local scale. It's called micro scale. Our research is focused on a local scale, not very large case, just a local scale. This case is very has a strong connection with the people, and as we see here. And actually, this kind of analysis is more or less like a fluid mechanic, like we see in the right part. We have high shear layer and vortex shading and the high low momentum region and the higher vortex. This kind of structure, turbulent structure, is very strong, and you need to identify in your analysis. So in this kind of analysis, we usually have two ways. The first part is obstacle resolving method, like what did in CFD. And another part is, I think some people involved may interested in the urban canopy model, but actually the urban canopy model may have used some exception, and this kind of exception is right or not. We need to find out which situation this kind of urban canopy model can be used better. And also we know that obstacle resolving may be time consuming. Some people think this kind of work will be time consuming. So we need to find out a better way to do this kind of analysis. So in this work, I have two objectives. The first one is the viscous contribution. I know in some internal experiment, the people working on the simplified urban canopy model may ignore the viscous contribution. So the viscous contribution can be ignored or not in this kind of urban canopy analysis research. And the second one is what's the spatial average flow features for inside the urban canopy, because this kind of results is really important for the people to improve the urban canopy analysis. So we think we can do some contribution for the community of the urban canopy layer. So in this case, we consider the different packing density, different flow direction, and the spatial arrangement. So the first of all, I think we need to do some validation, because these days I didn't see someone to show the validation results. As a modeler, I think it's really important to validate our simulation model before we forward our results. So in this case, I use very classical case. It's a packing density of 25 in a staggered arrangement. This kind of case, we have a lot of results from University of South Hampton and the University of Reading, Coasial, Castle. They are doing a really good results. So I want to compare with this kind of real data for our large area simulation. Here we can clearly see that if we don't use the mesh resolution enough, we can miss some kind of distance between the true mean velocity. And the second one is the standard deviation of the streamwise velocity. Actually, this kind of fundamental research usually ignored by the researchers, because they just mention the simulation is good, the model is good. But actually, I don't think so, because I really saw some work in BLM or research geographic research later. They use very close mice, but actually I think they didn't catch the standard deviation of the streamwise velocity. As you can see here, it's performed by the Castle and Ekbin, and they are using the LDV internal experiment. And we found that actually the numerical simulation cannot get such good results as the internal experiment. As a professor of Bohong in Sweden, and he mentioned that this kind of result may be due to the size of the simulation is too limited. But actually, personally, I don't think so, because the PIV data of the Kahin Blackman performed can also get this kind of difference. So I think this kind of problem is due to the mesh resolution. We can't get such small cell result. We miss the small cell turbulent structure. That's what I'm performing to move forward and increase the mesh resolution to get the 16-fold per cube to resolve this kind of result. Maybe we can see the result for next year. But this year we just show some some results we are getting now. The first one is the viscous contribution can be ignored or not. So we choose three cases: less dense, and largely dense, and the middle dense. As you can see here, we have two drag. The first one is pressure drag, and the second one is the friction drag. And we can see here, if we change the packing geometry of packing density, the viscous drag will increase, and especially when we change the velocity direction. Usually, we just have the velocity direction from left to right, and it's normal. But actually, when we change the velocity direction, we found that the viscous contribution increase largely, and especially in this kind of case, very dense, almost 44 and close to 0.5. This kind of case, the viscous contribution cannot be ignored anymore. That's really important for the Guangdong experiment and for the some researcher analyzed the simple urban canopy model. This kind of work has already published in the BLM, so it's very easy to understand why. Because as we say, in this kind of bicycle racing, the people will get a land because they can decrease the pressure drag. But actually, in this case, the viscous drag is increased. So in that case, the friction drag cannot be ignored anymore. So let's move forward. We want to analyze the spatial statistics of different kind of geometry. We compare our results with the palm. What we did is use open form, and what people did in the palm. We can clearly see that for the mean velocity, the open form and palm can get closer results. And for the velocity inside urban canopy, we can clearly see that if we decrease the packing density of geometry, the urban canopy model can show good results. But if the packing density is too large, the current urban canopy model is not good. Now, let's move forward, not just the mean flow and the standard deviation of the velocity and the shear stress and the dispersive stress. We can clearly see that the open form and the palm has a clear significant difference. That's very interesting because usually people think like the difference between these two cases is the same because they are also CFD software. But actually, we can see here the difference between these two cases is very large. It cannot be ignored anymore. And especially the dispersive stress, we can clearly see that in this case, it's the aligned case with high packing density. The distance between these two software is very significant, which means like the open form is a FUM method. It can control the conversation of the nature. But for palm, maybe they use the finite difference method. Let's will perform not very good. When the packing density, what we say, they have a lot of wall, the results may be not that good. Now let's move forward. It's the turbulent energy budget. That's what we did in 2000 before in publishing BM. In this work, we found that in this kind of packing density of 25%, there is a strong production of TKE in the vicinity of Q. And in this work, we just use just one geometric. So now we want to move forward, consider all kinds of variables. So I perform different packing density with light, medium, and high. We found really interesting like the spatial arrangement actually doesn't affect the TKE budget anymore, and it shows quite similar results, which means the spatial arrangement of the geometric not affect the TKE budget. However, the packing density play a very important role in this case, and especially in high packing density cases, that's very important because we have large city in these days, and the production of TKE budget and the dissipation is very small. Even we have very high and very large production in the shear layer. That's very important, which means if you have pollutant inside this kind of large city, high packing density city, the pollutant will keep stable and store inside the urban canopy. It cannot move out because it has a very large shear layer and strong production about the height of the urban canopy, which makes the pollutant, the air pollutant, keep stored inside the urban canopy. And now we change the velocity direction. We found that when we change the velocity direction, when we have high packing density, the mean velocity will change a lot and dispersive largely. But in some small packing density cases, the mean velocity looks very similar. It's really important because nowadays we want to use urban mechanics model involved. It's everyone wanted, but actually we don't know which case it can be better. But here is clear so the results that if we have low packing density in the city, the mean velocity will show quite close result no matter which wind direction. So we move forward, we not just use the idealized urban canopy anymore. We perform a real world to use the data. We do the measurement exactly in real world, and we choose a size close to the previous one, 6.25% packing density, and we can clearly see like the wolf data and the LiDAR data has a clearly significant difference inside the urban canopy layer. But if we use the meso scale to micro scale coupling method, we can diminish this kind of difference and show quite good results, which means the future is not just to use this kind of urban canopy model, and we can compare the meso scale model with the micro scale model, can get exactly very right results. And secondly, we can formulate the urban canopy model can show quite good results with idealized urban canopy model with different direction, and also the idealized cases. And also we look at the mean velocity in the inside the realistic urban canopy. We can clearly see the footprint by the high-rise building affect the downstream buildings, and the velocity will exactly affect by the arrangement of the geometry in the real cities. Okay, now let's get the conclusion. I don't repeat it, so I want to leave the time to the questions. Thanks.
Any questions? Thank you for the impressive presentation. I'm curious, you know about the numerical viscosity, artificial. How did you subtract from the real viscosity? Or you are present as the viscous contribution from the numerical viscosity?
Sorry, I don't understand.
Which viscous contribution you mean in your presentation? Is it numerical, artificial, viscous, or it's a real viscous contribution?
Actually, I don't understand exactly. Can you repeat?
If you perform the numeric CFD,
Okay.
you produce artificial viscosity, numerical, due to the solving of the Navier-Stokes equation.
Yeah.
So how did you subtract this artificial viscosity from your?
Okay. I see. Yeah. Understand that. Actually, in my cases, I use the obstacle resolving method. So the turbulent, I also use the periodic boundary condition. So we don't just put the inflow boundary condition. It's a periodic boundary condition. In that case, we don't need to think about the inflow turbulent anymore. The first thing. The second one is after that you are mentioning maybe the dispersion of by the numerical simulation. Actually, in my opinion, when we compare with the wind tunnel experiment, we think that our model exactly follow the results of the wind tunnel experiment and the DNS results. And in that case, the validation of the numerical simulation already showed the results is quite good. But otherwise, you will see the difference between by the minimized resolution or by the subgrid scale model or other factors or by the screens. So in this case, we not control the artificial dispersion anymore. We just control the setup inside the simulation. Exactly.
But okay, you can. Thank you.
Any more questions?
So when you obtain results with idealized sparse arrays, right? So you use isothermal conditions or non-isothermal?
Can you see?
Like, is it like idealized when you simulate idealized simulation, right? It's building blocks of they show different aspect ratio and different packing densities of buildings.
Yeah.
So do you use isothermal conditions like without like stability differences?
You mean the stability of the atmosphere, or
Yeah.
It's just the neutral cases, not high. Yeah, I'm working on these cases, but I didn't publish it here. Actually, we are thinking about add some temperature for the wall and for the ground, but here the result is just the neutral cases, so we can direct compare with the internal cases.
When you compare it with realistic urban canopy,
Yeah.
how come it's showing so much agreement when it's
Okay, I see. The realized cases we are analyzing is also compared with the neutral cases. We didn't think about too much about the atmospheric stability, but actually we were thinking about use a day with high wind velocity. We can see which day has a high wind flow. In that case, we have strong wind shear. In that case, maybe we can produce more neutral cases, so we can ignore the temperature thermal effect.